Welcome back, everybody, on this rainy day, the last day of the week. The topic today is to really try to get started with the optimization problem. However, what I would like to do before we start with the optimization topic, we are going to look at some other examples on how you can analyze data in project number one. So yesterday, we discussed a little bit in connection with project number one. We looked at the search for the optimal parameter lambda. So one of the things which you end up doing in basically all of these machine learning approaches is that you will have a set of hyperparameters. And this set of hyperparameters are typically parameters which we tune in order to optimize the score. So in project number one, the typical score is the mean squared error, or the R2 score. Now, if you want to automatize this, instead of doing this kind of brute force approach, which we have implemented in project one, where you simply set up a grid of these hyperparameters lambda, you could actually take and use a grid search, which is available through scikit-learn. So that's one possibility. And what many people actually do is to use this grid search functionality. So let me just show you how that actually, functions.
Is the polynomial degree a hyperparameter?
You can think, I would rather think of the polynomial degree as a model complexity. So you will,
Because when you say grid search,
but
we only have one parameter, lambda, for example. What is the grid? Isn't it lambda on the one scale and then model complexity on the other?
So if you think of model complexity, that is your specific model. When I say a grid search, what happens now, which we actually introduced that yesterday as a learning rate. So you would have a new parameter in your machine learning algorithm. And that means that you would have a hyperparameter typically, and you would also have a learning rate. And then you make a grid search for the optimal values. So now we are basically looking at a one-dimensional grid. In practice, you will have many parameters. The thing you're going to see, and we can understand that from the expressions as well, is that the most important parameters are typically the hyperparameter and the learning rate, which replaces the second derivative of your cost function. And these are normally the most important parameters. So many people would typically tune them first. And then when you're doing neural networks, you have additional parameters. You have parameters in the activation functions. The model for a neural network is the architecture of the network. So that would be the model complexity when you do neural networks. So here, the model complexity is the polynomial degree. So I would place polynomial degree as model complexity, and then look at the other parameters as parameters of your optimization. So in a neural network, which we're going to see pretty soon, then the model complexity is given by the number of hidden layers you have and the number of neurons or nodes you would have in every hidden layer. So that's the model architecture. Okay, so the examples which I just wanted quickly to show you are examples which you will find at the beginning of the day today. So if you scroll down here, you will get to Friday. And there are some examples on here on actually how you can use this grid search. And if you now look at what we have been doing, like in the first code here, you probably recognize this function, which I use again and again. And in this specific case, I'm not using an intercept, and I'm performing just a plain, straightforward implementation of ridge regression. And in this case here, when I have a lot of noise, it actually looks like this. So if I were to take, this is also something you will notice when you run your own calculations. If I now take away the noise here, so let's do that and just rerun it. then you will see something like this. So typically when you don't have any noise, it's actually ordinary least squares which does the best job. And in this specific case, you see a perfect fit to the data, basically. When you add noise, then you are not guaranteed that ordinary least squares will actually give the best mean squared error. So these are things you will have to play around with the different hyperparameters. So this is the kind of fit we would do, how to say, by the eye. I mean, you run the calculations and then you say, okay, I can see for these values of lambda, we seem now to have the best mean squared error. And in project number 1, we don't expect more than that. But if you want to dive into more advanced things, you could actually use, let's say, the optionalities which you have in scikit-learn. So scikit-learn offers you a functionality here, which allows you to perform this grid search. So this is basically the same function. So there is a grid search here where you plug in your test values and you perform a optimization. So you have a grid search, and this does also, it actually does cross-validation for you at the same time. So it contains both a grid search for the optimal value of lambda, the hyperparameter you have, and it finds also the optimal estimate for the mean squared error via cross-validation. This does by default, I think the default value is 5 folds. So if you go into the scikit-learn manual, you can actually find how to increase the number of folds. So the only difference here is instead of performing my standard ridge regression, I do actually now transfer my model, which is ridge, and then I transfer the values of lambda, and I then perform a grid search. So the grid search now is done on the values of lambda. So what I could do now is to take away again the noise. So let's do that and just perform. It's the same case which we had in the previous case. And here you see now that since I started with a lambda which was 10 to the minus 4, and if you remember the figure which you had here, without any noise, then when I start at 10 to the minus 4, my mean squared error is basically 0. And you see that reflected here as well, and it finds that the best lambda value is when I have 10 to the minus 4, and the best mean squared error. So this is doing what we expect when we have no noise. Then you can change the noise and make life a little bit more difficult. And if you add noise, then as you saw from the previous run, where we just did the by the eye search, you see now that the value it finds the best estimated value among the values you plugged in to be a 10 to the power of 2, and then it finds the best mean squared error. So depending on whether you have noise or not, this grid search will try to find the optimal value. Remember also that this actually does cross-validation for you at the same time. But this is a pretty useful thing to do if you want to compare your code with this optionality. Now feel free to use this functionality. And at the end, we will always try to do some kind of grid search for the optimal values. There's also another functionality which is called a randomized grid search. You can take a look at that one and the functionality of it. We're not going to go through that much, but it's called a randomized search with cross-validation. You transfer your model, which is ridge regression, and then you can try to figure out the optimal values. So try to play around with these functions and look also up their definitions here. We are not going to discuss in this course the algorithms behind this randomized grid search, but you should know about them because they can be pretty useful. Now, the thing I wanted to do now before we continue with the optimization problem is actually to remind you of what we did yesterday when it came to logistic regression. So what we started with yesterday is to see how we can apply machine learning, and in our case, logistic regression is actually a deterministic algorithm at the same footing as linear regression, but we are going to do a classification problem. And the easiest case to look at, and the most common case, is actually a binary classification problem. The typical yes, no, true, false, 0, 1, and so on. So what we did yesterday was actually to derive the equations for logistic regression for a binary case. And you can extend that onto more classes. So let me quickly remind you of the basic steps which we implemented yesterday. So we have two events only, one true or false. So that means that yi, your observation, is equal to 1. In many cases, you will actually have data where you have encoded information like true, false, and then you have to transform it to numbers. When you have more categories, normally what people do is to transform these ones into bit strings. And we will see that in the examples when we are going to develop our own neural network code, when we are trying to recognize handwritten numbers. There's a famous data set for that. And then we will have to transform the information of every handwritten number into a kind of bit string. But this is a typical way you would do it. And by the way, there's always this kind of thing with looking into the data set. Now, many of the data sets which I'm running in the lectures, they are already streamlined for usage with scikit-learn. So that means that sometimes you don't see the data themselves. But when you dive into a real data set, it's always convenient to look at the data set, because some of the data may actually be punched in wrongly, because often there is a human which actually punches in the entries. So sometimes instead of 0 and 1, that human could have punched number 2. So it's always useful to actually traverse the data set. Actually, we had a case of scientific fraud in Norway, which is perhaps one of the worst ever. And that was in medicine on cancer in the mouth. And all the data were faked. And if people had looked into the data sets, they would have seen basically that there was basically the same name which appeared again and again, or same names all the time. That was a horrible case of scientific fraud. And it happened in 2005, 2006. I don't know if you've heard of that. And if you're interested, we could discuss about it during the break. It was published as an article in a famous medicine journal, which is called The Lancet. And some of the people had actually gotten funds from like the American Health Research Organization of millions of dollars. And all the data were just faked. And some people had even signed that they had done the statistical data analysis, but actually the person who was responsible for the faking of the data had also faked the signatures of the co-authors. But when you get an article in a famous journal like The Lancet, I mean, nobody complains. And then you're happy, okay, I have an article in The Lancet, which is like Nature, something like that. But the case was really a bad case of scientific fraud. But if people had then just looked into the data file, they would have seen that there must be something wrong with this data file. Okay, but trust is an important thing, right? So you trust people. Anyway, that was a small digression. So what we did then was to define these probabilities. And what we did was to replace standard linear regression, where we have a function f of x, a continuous function. We replaced that one with a probability. And one of the simplest models for these probabilities is what's normally called the sigmoid or logistic regression function. Not logistic, but the logit function. So this sigmoid function here is something which we are going to encounter again and again. We have two possible events, and if we sum up these two probabilities, these sum up to 1. So the probability should be normalized to 1. And it's also easy to see that this function here can be normalized. With those definitions, what we did next was to make a model for the maximum likelihood. And the parameters beta, so D is a domain of events which we have, and beta is, as before, is the parameter which we have. In this case here, we're just dealing with two possible parameters, a beta 0 and beta 1. And then we define the cost function to be either the positive logarithm or the negative logarithm. And we could rewrite this function in terms of simple parameters here. And then we took the derivatives. And these are the derivatives which we want to use to optimize and find the best value for beta. Now, the problem which we face when we now take the derivatives is actually that these parameter p, they don't have a linear dependence on beta, the unknown parameters beta. And then we are not able to extract a nice, analytical expression for the estimators beta or the parameters beta, as we did with linear regression. And that means simply that we now have to recur to numerical solutions. And this is the main topic. And as I said yesterday, if you can cook up a smart way to optimize these functions, because you're going to do this again and again. So this logistic regression case which we are dealing with is actually a small problem. Normally the matrices we deal with, they end up being perhaps 100 times 100. So it's pretty easy to run and obtain results within a decent amount of time. But as soon as you move into neural networks, you're going to have millions of parameters. And then clearly we want to optimize millions of parameters, and that's going to be expensive from a numerical point of view. And that's why being able to find the gradients and optimize the parameters through the gradients is something which really is at the heart of basically all the machine learning algorithms you're going to see. And again, being able to speed up these different algorithms for finding the gradients is something which is really the real bottleneck, I'd say, of basically all machine learning algorithms. So we're going to spend a little bit of time in order to develop your intuition about the optimization problem. You can easily extend to more predictors or features. So we've been calling these features, predictors, or properties, depending on the context. So you could have, like in the cancer data, which we're going to look at now, you will have something like 30 predictors or features. And then you can easily extend it, and you would have different parameters in front of every predictor here. And you can include more classes, and this is something which we will discuss a little bit more in detail when we move into neural networks. You can extend this sigmoid function or this logit function to include more classes, and you're not limited only to the binary case. And I just invite you to take a look at it, and then we are going to look at this more closely when we move into neural networks. And this function, which you see here, is normally called the softmax function. But we are coming back to this topic a little bit later. We are not going to use it now, because now I wanted to present to you a famous data set, which many people have studied, and it's called the Wisconsin cancer data. So this data set is already included with scikit-learn. So there is no stress for you in actually taking the raw data file and transforming that one into an appropriate format for scikit-learn. So everything is done behind the curtains for us. Feel free to use these examples. People have actually used these data sets in project number 3, also project number 2. And if you're interested in this kind of related problems, it's actually quite useful to actually look at this example. There is a lot of scientific literature around it. So the data set contains, I think it's roughly 500 patients, and they classify it's a yes-no problem. So they classify whether this is a benign tumor or it's a malignant tumor. That means not benign. So that's the case you want to avoid. And it has something like 30 features. So features like the size of the tumor, the perimeter of the tumor, the area of the tumor, and so on. And these are features which a pathologist would typically look at and say that most likely this is a benign tumor or this is not a benign tumor. So the output is just a yes, no, or ones and zeros. And the data set here, if you want to classify that with logistic regression, I'm just highlighting a little bit the way you would do that with scikit-learn. In project number 3, we actually want you to implement logistic regression with your own gradient descent or optimization code. And then one of the data sets you can use is actually this data set. So we take away the, the problem with transforming the data. And then you can use all the functionality of scikit-learn. But here, if you look at the way you would use logistic regression, you would simply call the module with logistic regression. And in this case here, there is a solver. So there are sets of solvers for actually solving this Newton-Raphson type of equations. And this LBGF stands for Broyden, Goldman, Sachs, something. I never remember all the authors. There are actually 5 authors. And that's one of the more popular ways of implementing a quasi-Newton method. And we are coming back to that next week, what these actually mean. So there's a different class of solvers. And this is one of the more popular ones for finding the roots of functions. And it's very efficient. You need very few iterations to find the results. And then you, when you've done that, you can actually take the calculate the accuracy of your test on your test data. And in that specific case, there is a score function, which actually what it calculates now is the accuracy. And I'm coming back to a little bit what this means. What kind of ways how do you actually define the accuracy? Because now it's not the mean squared error we are presenting. So what it means is actually that it tries to see how you classify what we normally call true positive and true negative. So these are the correct values you want to classify. We're coming back to this. And you simply sum up all the correctly classified events and divide by the total number of events. So if you classify correctly, this accuracy score is 1, right? So if you have 100 events and you classify all correctly, it's 100 divided by 100. If you are not classifying correctly, you may have less than 1. So this is called the accuracy score, and we are coming back to that a little bit later. So now it's no longer the mean squared error, right? So we have different ways of assessing the quality of the model. So here, if you just run it, then you will see now that this is my test data. These are the number of features. Now this is the train data, number of features. This is the test data and the number of features. And the test accuracy, so which is simply the number of correctly classified events divided by the total number of events, you're reaching here 96%, which is actually pretty good. So this tells you that if you can get away with logistic regression, use logistic regression. And the same is if linear regression does a good job, there is no point in using more complicated methods like neural networks. If it does a good job, it does a good job, right? There's no point in complicating life, right? So you can see here, this is actually a pretty good result. Now, there's another thing which I wanted to highlight to you. And you may remember in the beginning, we talked about the so-called correlation matrix, which is actually you calculating the covariance and you scale it by the variance. And this is a quantity which varies from -1 to +1. And if it has a value of 1, it means that you have a high degree of correlations between the different features. If you have 0, that means that this feature doesn't correlate with that feature at all. So this is something which, if you have not too many features, like in this case you have 30, it's extremely useful to plot the correlation matrix, because that tells you, which of the data points may be more interesting. So if you now look at the correlation matrix, there is also another functionality here which I've done, and that's to calculate the, sorry. So if you look at this figure here, that calculates the number of benign and malignant tumors, and it gives the frequency of them as a function of the different features. You see the mean radius is one of the features. You can see the mean perimeter is one of the features. The mean area is another feature. Then you have something, and then you have other features which I cannot explain to you, which are more discipline-based, and a pathologist can obviously make much more sense of it than I can do. But what you see here, if you look at this plot, which is also a very useful way to analyze your data, when you look at the frequency of these yes and no cases, so it's only a binary system, so it's much easier to plot. So if you plot that frequency, what you see now is if you look at the mean radius, there is very little overlap between the benign and the not benign case. So that could tell you that the mean radius is a good kind of parameter or feature for telling whether this is a benign tumor or not. If you then look at other properties like this mean smoothness, there you see a much larger overlap between benign and not benign cases. And then you could say that this is perhaps not a good indication of you being able to sort out what is a benign or not benign tumor here. So this is it's a very useful feature when you are studying your data. So as I said, look always at the data. That's something which is extremely important. If you can, obviously. If you have zillions of data, then it's almost impossible. So this is one of these examples which contain a lot of this. You can see here you have other, so the perimeter error. And you would typically say, since we know that the perimeter is proportional to the radius and the area is also proportional to the radius, you would expect, if you now calculate the correlation matrix, that these would be correlated, right? And if you then look at the correlation matrix, this is a little bit dense, right? But you can see now this is the mean radius. This is along the diagonal is always 1. But you see now the mean area, which is this one. There's a correlation of 1. And if you look at the mean perimeter, there's a correlation of 1 between the mean radius and the perimeter, which is reasonable because, I mean, the area is proportional to the radius, with the radius, and the same with the perimeter. So you will see some features which are strongly correlated and some which are less. This is also, even though it doesn't give you this kind of insight about the learning process, it gives you a useful bird's view on the data. And you can really, from these few things, like this first plot and the correlation matrix, you can infer something about which data perhaps, or which features are more interesting than the other ones. So this kind of analysis is something which we typically do when we analyze our data sets. So the examples on how to use but there are other ways of classifying the data. And there is another package in scikit-learn, which is called scikit-plot, which allows you to introduce other types of metrics. And I just wanted to bring up some of these metrics on the whiteboard here so that if you haven't seen this before, this is actually a useful way of presenting classification problems. So one of these quantities is actually the confusion matrix, which takes your test and your prediction. And then there's another one, which is called the ROC curve. And then there's the cumulative gain curve. And I just wanted to explain what these quantities stand for so that they just don't come as like a bolt out of the blue here. So one is the confusion matrix. And for this binary problem, what you would do then is actually to present true positive, true negative, false positive, false negative. And this is a way to actually typically present your data. So if you run that, what you would see, by the way, you will often get messages like this, a number of iterations. This is your solver for optimizing the derivatives, which then hasn't converged properly. So if you get a flag like that, you may have to increase the number of iterations for your solver. And we are coming back to that pretty soon now, but I wanted to go through these practicalities here. So one of the things you can get then is this confusion matrix. And you can see now this should be true positive. So 98% of the true positives are correctly classified. This should be true negative and 94%. So you would, and what you end up with when you look at your accuracy score it's normally the sum of these two here. And this one would be true negative, and this is no, true positive, and this is true negative. You can also plot something which is called the ROC curve, but before we dive into that one, I just wanted to give you some of these definitions so that you can actually make some sense out of it. So let me just bring up these definitions before we move on to the optimization problems. Just have to find back where I actually did put it. So I have, I just need to find my notes here. Yeah, here we have. So let's just switch to the whiteboard here and discuss these features which are used not often to present the quality of a given model here. So you will often see these kind of acronyms in the literature. So TP, which normally stands for true positive. So this is what you would say with equivalent with a hit, or that you have classified correctly the positive events. So in our case, we have zeros and ones. So what you define as positive or negative, that's up to you, right? So you could put positive, set that to 0, negative to 1, or the opposite. So you just have to make the selection here. And then you have a true negative. So this is a true negative. And that is equivalent with correct rejection. So in our case, you would obviously define a benign tumor as, I would say that's true positive. Some people call it true negative, I don't know why. But I would say that a benign tumor is a true positive, and a not benign tumor, malignant tumor, would be a true negative. So that's the way I would think of the data here. And true negative equivalent with correct rejection, so, or negative result. Then we have a definition of the accuracy score. That's one of the standard scores which you would see, accuracy. So in that case, what you would have is the sum of all the true scores. So I'm just going to write some summation sign. So this is a little bit schematic mathematics. The summation of all the true scores plus the summation of all the true negative ones divided by n here, where n is the number of events which you have, or outcomes. So this is the one of the most common types of scores which you will see in the machine learning literature. Now, what happens sometimes is that your data is skewed. That means that you may have many more true events than positive events, no, and negative events. So true positives and true negatives. And in that case, people tend to use other types of measures for the quality of the fit of your data. And we are going to meet some of them a little bit later. So the other type of quantities, so this is the accuracy score, that's a pretty common one. And then we have different combinations of, like when you saw this confusion matrix, we have something which is called a false positive. And that's an equivalent with a false alarm. That's one way of thinking of it. We have a false negative. That's obviously the next one. And the confusion matrix, which you saw now, so that's normally equivalent with a miss of the negative events. So the typical data representation which you would see then is this confusion matrix. And the confusion matrix would typically then have something, look something like this. In our case, we have a binary problem. That means that we would have a true positive here. We would have a true negative. And then we can have false positive. And then we can have false negative here. So that's a typical way you would then display the data for this binary type of problem. So you saw first the accuracy score, which is the most common one, and then you have the confusion matrix, which is also pretty common. And then you can now start making combinations of these, depending on how you want to visualize the data and what gives more meaning and less meaning. So like this ROC curve, which is another way of presenting the data, means that you need to present to define some other quantities. So let me give you some of these quantities here. So there's something which is called the precision. And when I'm now writing it like this, I'm assuming that I'm summing over all the true positive events and divide with all the true positive plus the false positive. So this looks at the positive events. We have something which is called the true negative rate. Which is simply equal to, so this is normally written as a TNR, and that's simply Tn, all the negative ones divided by the total number of data. So n is the total number of data which we have. We have many other of these. There's something which is called the recall, and that's given by the true positive ones divided with the true positive plus the false negative. So sometimes I actually have to really rethink what this actually means. If you look at this ROC curve, which we had in one of the slides here, this has the name of a receiver. It actually, I think it originates from ways to classify phenomena in electromagnetism, in radio tech. I don't remember exactly. I have to look it up again. I mean, so receiver operating characteristics. I'm always able to confuse myself. So this is the actually what you plot then is the true positive rate. And that's plotted against the false positive rate. So you will find many such ways of actually presenting the data. The other one which you saw is something which is called the gains curve. And that is actually the number of counts of true positive plus the number of counts of false positive divided by the count of all observation. So this is your data. So these are different ways of displaying your results. And you will encounter many more of these ways of describing the data. But the most common one is actually the confusion matrix when you're doing this kind of classification problem, because the confusion matrix gives an immediate view on the quality of your fit and your model. So with logistic regression on this data set, we are getting close to 96%. Later, we will see that when we use methods like boosting methods, random forests, and so on, we will actually get a precision which is equal to 100%. But this is actually not so bad for a method which now did only fit 2 parameters. Actually, it fit more parameters because we have 30 features. But the model is based on this simple approximation of the probability P of X, which is given by the sigmoid function. Okay, so what I wanted to dive into now is more the discussion of these gradient methods. Yeah? Could you say it again? Yeah, so it's actually, I could just have, because this TP can stand for, I could write it like TP with the sum of all of them, or I could just say that this is the total number of TPs. So it's, I was a little bit sloppy with the notation here. So in a certain sense, I should have stayed with the one which I used up in the beginning here. So this is the total sum, and this is the sum again, plus the sum of these. So all of these actually implies sums. So maybe it's better actually to write the sums here. So let's just do that. I mean, that's actually better. Yeah. Plus that, and then plus n here. I think that's a better notation. Yeah. So sometimes, like me, I actually sometimes I get confused when I look at many of these figures because I always have to think, what does it actually mean? And it takes me some time to readjust. And I think the simplest one for me is a confusion matrix. I mean, that says everything to me, basically. Okay, so what I wanted now is to go back to the gradient problems and the optimization problem. And that's going to keep us busy also parts of next week. And as I said, if you can cook up new methods here, I mean, you're going to definitely be pretty popular. So let's now look at where we ended yesterday. But let's now take a look at the cost function. So suppose now that we have a cost function which we Taylor expand. So there's another way of deriving the same equations which we did yesterday. So we have the cost function now at an optimal value beta. So let's just assume now that we Taylor expand the cost function around this optimal value. So we Taylor expand it. And now I'm just going to introduce some shorthands here. And we're going to Taylor expand it around the values, the difference actually between the beta and the values from a previous iteration, a beta of n. So n stands for iteration n. But it could be, this doesn't need to be an iteration. It could just be a value which we are expanding the cost function around, given that we have the true value or the best optimal value which fits the data for us. And beta hat is the optimal estimator. So if you Taylor expand, what you would get then is obviously a C of beta of n. So we know the value. So we assume now that we know this specific value. Then we need the gradient of the cost function. And what we defined last time, so let me just bring up that. So we have the definitions. So dc of d of beta with beta equal to this beta of n. This is something which we defined as g, the gradient, at iteration n. So when you see this g of n, that's just a derivative calculated at that specific value of beta. So the problem which we face is that in our case, we don't have a beta value which has a linear, the equations don't have a linear dependence on beta, and then we have to revert to numerical solutions in order to find the optimal beta. So let me just quickly finish this one and then we take a break. So this is now, remember now that betas are vectors and G is also a vector. And then we had that the second derivative, d of C of d beta, and then we have the beta transpose, is given by this Hessian matrix. And this is also evaluated at a beta value equal to beta of n. And we are going to write this as an h of n here. So what it means then, when we calculate these quantities, we are going to have a g of n, and this is being transposed. So these are actually vectors, and we are calculating, we are performing the Taylor expansion of the cost function, which is a scalar. So when we are multiplying with vectors, we have to take the transpose of one of them, and then we multiply with the vectors beta minus beta of n, like this. So let me put this in a box here, because this is just an aside. And then what we get next, so let me just put this one in here, plus, and then I have a factor of a half. So this is the second derivative. And now I'm going to get this beta hat minus beta of n transpose multiplied with the Hessian matrix, or the second derivative. And this is again multiplied with beta hat minus beta of n. And this continues. So this is the Taylor expansion of the cost function for an expansion around the difference between the optimal value and the value from a previous iteration. So after the break, we're just going to manipulate these expressions, and we are going to see that this actually leads to Newton's method when we stop at second order here in the Taylor expansion. And then we're also going to look at what is the optimal ratio for this Hessian matrix with respect to the gradient in order to achieve a decent convergence of the method. So we are going to solve things iteratively, and that means that the equations may not converge, or they may converge very slowly. And that's going to be one of the bottlenecks in basically all machine learning algorithms. So we are also we have to deal with a quantity, this Hessian matrix, which becomes pretty large. And since we are doing this repeatedly many, many times, we want to avoid to evaluate this matrix. And what we normally do then is to replace this matrix with a parameter, which we tune. Okay, I went a little bit over time. I just wanted to bring this up. And then after the break, we are going to go more into the details and look at some simple examples. So I'm going to put the recording on pause. Okay, so what we have done now is simply to make a Taylor expansion. And I just wanted to show you an alternative way by which we can actually derive Newton's method. So we assume now that we made some small changes to this vector beta. And then at the end, after a set of iterations, we are approaching more and more the value which we want, the optimal parameter beta. So if you now look at what we have here, we could now redefine. So I'm going to just define a new vector b, which is beta hat minus this beta of n. And that means that I can rewrite my cost function, this c of beta hat, in terms of this constant, which is now calculated at beta of n, which we know. And then what we have then, so this parameter b is actually a parameter which in principle depends on n, number of iterations, but I'm just going to leave it out. So I'm just going to write b here. So we can rewrite this now in terms of this g of n, iteration n, the transpose of it multiplied with b, plus 1/2, and then I have b transpose times my Hessian matrix, the derivative calculated, the second derivative of the cost function calculated that specific value. So remember now that b depends on n as well, because it depends on the parameter beta of iteration n, and plus here. So if we stop at second order, you see now that this looks like a function like f of x equal to a constant plus, and this is a familiar function which we often encounter in the literature, where we have a constant and then we have a quantity gamma of t multiplied with x plus 1/2 of xt of a times x, where a is the Hessian matrix and this gamma is the gradient in our case. So this is a typical problem which you often encounter in optimization problems. And then you take the derivative of this function and you want to optimize that one with respect to the parameter x and find the roots of that specific equation. And this is essentially what we are doing now. So when we then take the derivative with respect to the parameter beta here, what we end up with, so what in this case we are going to calculate the derivative of d of c with respect to this parameter b. This is a quantity which we now take the derivative of. And if we do that, what we end up with is the following. So what we find then is, and these are, remember now that these are matrices and vectors. So I'm going to get a G of n plus, and then I'm going to get a matrix H of n multiplied with this vector B. And I want this to be 0. So that means that my quantity B, which is the unknown quantity, which in my case is actually beta hat minus beta of n, this is actually equal to minus, and then I have my Hessian matrix inverse, and I have to put this n in here. So this is the in, let me just rewrite this a little bit better. So this is h of n, depends on the value beta of n. It's the inverse of that one multiplied with the gradient at iteration n. And when we now shuffle over beta of n, we have now the optimal value, which we can rewrite as a beta of n plus 1. So we have reached the optimal value at iteration n plus 1. And this is simply equal to beta of n minus, and then we have the Hessian matrix, the inverse of that one, multiplied with the gradient of n. And this is the derivation of the same equation which you saw yesterday, but now making a Taylor expansion of the cost function around the optimal value. Now, there's something which we can do in addition to this, some simple analysis, which can tell us a little bit about how we can understand the optimal values of this matrix H. Now, we don't want to calculate H. So what we typically do is that we replace H, as I said yesterday, which is the second derivative of the cost function. There are actually many ways of estimating this parameter gamma, and we are going to come back to that, but we replace that with a parameter gamma. So that means that the iteration n plus 1 is now going to be given by this iteration beta of n minus gamma multiplied with the gradient after the nth iteration. And this parameter, as we said yesterday, this is a parameter which in the literature is normally called the learning rate. And that becomes a new hyperparameter. And in many applications, it's actually cheaper from a computational point of view to set up a set of values of gamma and simply play around with them and see what gives you the best mean squared error. Because sometimes the derivatives, the second derivatives are very expensive to evaluate because you have to invert a matrix. And like in this cancer case, which we saw before the break, you would have 30 features, which means that your Hessian matrix would be a matrix which has dimensionality 30 times 30. So every time you do an iteration, you would have to invert a 30 by 30 matrix. evaluated at the value beta of n. And this is something you want to avoid. So this is one of the new parameters we are going to play around with. And in order to get some insight here, we can actually see if we can try to relate this to the Hessian matrix. So let's take a small detour here. So let's now expand the cost function, C around beta of n. So this specific value which we have, minus gamma times g of n. So let's perform such an expansion, a new Taylor expansion. So you will see many Taylor expansions here. So what we get then is a C of beta of n minus gamma of g of n. So this is actually the new optimal value. Remember now that this is, so we're actually repeating the same exercise which we had before. So this is beta of n plus 1. Nothing but that. So this is going to be C of beta of n. And then I have the first derivative. So we have a minus gamma. So we have minus gamma. And now I'm just dropping the parameters n, or we could rather keep them. Let's keep them. T times g of n. So I'm just plugging in the terms in the expansion here, in the Taylor expansion. And then I would get them plus 1/2, then I get a gamma squared, I get a g of n transpose multiplied with a Hessian matrix for iteration n, and this is multiplied with g of n, and then we have higher order terms. Now if we then do the same thing and skip the higher order terms, now we're asking ourselves, which is the optimal gamma which makes this expansion converge? So in this specific case, so gamma is just a parameter. So how do we find the optimal gamma here? So we are assuming now that this C of beta of n is not a function of gamma. So I'm simply calculating the derivative with respect to gamma of this cost function here. So what I do now is to take the derivative, and we want that one to be 0 with respect to gamma. And that means that what we get then is a function which now contains g, and I'm going to use a shorthand here. G of n goes over to g, and h of n goes over to h. So what we get then when we take derivative of the first term, assuming that it does not depend on gamma, we simply get a term which has the gradient transpose times the gradient plus the 2 times gamma times the gradient transpose times the Hessian matrix times the gradient. So that means simply that what I get then is that gamma, when I take the derivative, I get a gt of g of t times h times g. So I have a way to estimate the parameter gamma for every iteration. But that means that I have to calculate this gradient times the Hessian matrix times the gradient transposed. And that involves a lot of floating point operations. So just keep that in mind, eh? But this can allow us now to say something. So if you now think of this in terms of a Taylor expansion, what you want in terms of a Taylor expansion is that this series should converge quickly. So what does that say about the ratio here? What does that say about the denominator which you have? It should not be larger than the numerator, right? So you can run into problems when this quantity here, when this one is larger than the numerator, because then you can have a coefficient in front of the different terms which is larger than 1. So you have a gamma squared, and then you have a gamma cubed, and so on. So it depends very much on the values of the other terms, obviously. But as soon as you have a parameter which is larger than 1, this can lead to problems. Now, there's another thing we can look at here. So we can make an assumption, and you can now assume that these G's, by some reason, are the eigenvectors of H. So let's just make that assumption. So assume that G, so if I multiply H with G, I get an eigenvalue times the eigenvector. So if that is the case, then what you find is that gamma is equal to G times G divided by lambda times G, and that's simply 1 over lambda. And now you know that the matrix has some maximum values for the eigenvalues and some minimum values. So that means that in our case, gamma min is actually 1 divided by lambda max, and gamma max is equal to 1 divided by lambda min. Now, there are some statements here which are very important for us, and we are going to see that now when we run some numerics. So I'm just going to state this, but these are theorems about the convergence of these methods. So you can actually use the singular value decomposition theorem on the Hessian matrix H. But I'm just going to state the result here. And I'm not going to prove it. So what you can show, if we analyze the Hessian matrix, so the convergence of this Newton-Raphson scheme, of the scheme, and how fast it converges actually, is given by a condition, which is gamma less than 2 divided by the maximum eigenvalue of lambda, of H, where lambda max is the largest eigenvalue. Largest eigenvalue of H. So if you can diagonalize the Hessian matrix, that can actually tell you a little bit about what you should choose as a variable gamma. Yeah. Cos'è? So I just made an assumption. It's normally not the case, right? But you can use the singular value decomposition on the matrix H, and then you can show that there is a condition on the parameter gamma for convergence of the iterative procedure. But what I did here, what I did up there, was simply just to make a plain assumption that G was the eigenvector of this matrix H. But that doesn't need to be the case. Yeah.
Doesn't H depend on beta?
Yes.
So then H changes.
Yes, exactly. And that's, so for those of you online, in the calculations which we did here, I suppressed the fact that H actually depends on the parameter beta at an iteration n. So if you want to use this recipe, you would actually have to change your gamma for every iteration. And that becomes expensive. So you see the kind of bottlenecks with the optimization part is actually related to the calculation of this second derivative, which enters your Newton scheme. And basically all the kind of solvers are ways to circumvent this problem. So this method, which you saw before the break, which had the acronym LB, and so on, I never remember all the name of the authors, that's a method which tries to estimate the Hessian matrix at every iteration step without calculating it. So you have to excuse me a little bit if I keep repeating some of these simple things, but I think it's an important thing to be aware of, that when we do machine learning, what we normally implement is actually this Taylor expansion of the cost function around the optimal value, we keep the terms to second order, and from that we can derive this Newton-Raphson scheme. And then this is the typical scheme we want to implement in order to find the optimal parameters beta, or the optimal estimator. And you can actually run this analysis, and you can show that in order to ensure convergence, there is actually a criterion on this parameter gamma, which then depends on the value of the Hessian matrix, or the eigenvalues. And the way it's going to converge, you can also relate that one to something which is called the condition parameter, which is the ratio between the largest eigenvalue divided by the smallest eigenvalue. And that's something, if they are very different, these two eigenvalues, the minimum and the maximum, then normally the convergence rate is much slower. Okay, so what's actually going to come now is a set of, implementations of the simplest possible way we can actually set this up and control that what we are doing is correct. So we're actually going back to some of the exercises we did in the beginning of the semester, where we used linear regression. And then we are going to implement the gradient, and then using a learning rate and just play around a little bit. And these are so simple examples that we can actually calculate the Hessian matrix and its eigenvalues immediately. And then we can try to tune the values of the parameter gamma. But I just wanted to remind you of some other things which deal with the kind of optimization problems which we end up with. So if you look at a general problem, let me quickly remind you of some of the basic properties when we try to optimize problems here. And if you now look at the type of functions which we want to optimize, so if we now do this in 2 dimensions, so we would have a function which depends on x, f of x. So the typical problem we want to deal with is actually to find a minimum. Alternatively, we can have a maximization problem. Like this, so a maximization. The type of data which we often end up with are data points which may not exhibit this kind of nice behavior. So if we now still stay in 1 dimension and look at a function f of x as a function of x, the kind of data we may have could be something like this. So where we would like to end is actually here. So this is something which we would call the global minimum. Here we have what we might call a local minimum. And we could actually be stuck there. So these optimization algorithms are algorithms which typically, if we would start in a random position and we start here, and then if we reach this minimum, then the algorithm would just simply place you there and you would not move out of that minimum. And you would simply just stay there. Similarly, this is also a local minimum. What you have here is a local maximum. And then you have some nasty places where you normally don't want to stay. Does anyone remember what you typically call these type of points, which you see there? That's a saddle point. So these are also points where the derivative is 0, but where you are in a kind of unstable situation. So this would be a saddle point. So many of these algorithms, which we are going to discuss, they try, especially when we look at something like stochastic gradient descent, they try to avoid this problem of being stuck in a local minimum. And the idea then is to try to distribute the starting points in a random way so that you can actually reach, hopefully, this global minimum here. But just keep in mind that even though this is in one function, in a one-dimensional function, many of the cost functions which we are going to deal with are going to be really multi-dimensional animals. And there's no guarantee that there is a local minimum or global minimum. So that's some of the problems which we don't know a priori. The cases we have been looking at with linear regression and logistic regression, they have a second derivative which actually leads to a matrix which is semi-positive definite, which means that the eigenvalues are essentially equal to 0 or larger than 0. And when we do ridge regression, the eigenvalues are always positive, which means, translated into the kind of convergence criteria for optimization problems, that means that you will actually reach a global minimum. And actually, there's a global minimum. So the kind of problem which we face is actually a problem which more looks like this figure here. But let's try to gain some kind of intuition by developing some simple examples here. So let me just move back to the slides and the Jupyter book. So in the Jupyter book here, if you scroll down, there's first a repetition of the equations which we have been looking at. So this is the way we would typically implement the Newton's, ideally we would like to implement Newton's method like that. So this is a Hessian matrix, where we discussed this matrix W yesterday, which has only diagonal entries. And then we have the gradient, and then we have the old value and the new value. So if you just scroll down here, you will find a repetition of basic properties of Newton's method, which we have been discussing now. There is also a quick reminder about convex functions. And I just invite you to take a look at it, because many of you have probably seen that in different math courses. So I hope you don't get offended if I don't go through a reminder on convex functions, but just take a look at it. There are basically some definitions of and conditions on convex functions here. But what I wanted to do now is more to discuss the first example, one of the first examples which we looked at in this semester. So as I mentioned, project number 2, you're going to replace the calculation of let's say the linear regression equations, where you have an analytical expression for the parameters beta. You're going to write your own gradient descent method. So now we are going to play around with this simplest and poorest method, where we replace the second derivative with a parameter gamma, the so-called learning rate. And the idea then is that in project number 2 is that you can then, 1, compare that with what you got in project 1. And then when you see that your own gradient descent method is functioning well, then you know that, okay, then I can apply it to more complicated cases, because you will need that when you're going to implement a neural network. And you're going to need it when you're going to set up your own code for logistic regression, because then you have to solve it numerically. So it's a way to step you through the basic elements which you will need in project number 2 as well. So here we have a very simple function which we looked at in one of the first homeworks. So we produce some x values, and then we have y, which has some additional random noise. And we want to make a fit in terms of a first order polynomial. So we have just 2 parameters. With 2 parameters, it means that the Hessian matrix is a 2 by 2 matrix. So it's pretty easy now for me to actually calculate the eigenvalue of the Hessian matrix. So let's just look at what happens here. So this is the design matrix. I have kept the intercept, and these are the points. I have 100 points. So this is basically my design matrix, as we have been discussing now in connection with project number 1. And then the cost function is pretty simple. So I just have beta 0 and beta 1. So this is what it looks like for this number of points. So again, this is just a kind of reminder of what you're going to see, or what you see in project number 1. And then you take the derivative of the cost function. And in this case, the only thing I've done, instead of having a minus sign, I just flipped y and beta. So that takes away the minus sign. So this is just you just rewriting the gradient. And the gradient is now simply given by this 2 over n. I have the sum, this is the gradient for beta 0 with respect to beta 0, and this is with respect to beta 1. And then you calculate the Hessian matrix, which is a quantity which now is simply given by the x transpose times x, and is given by these second derivatives, which you see here. So this is the way you would calculate the Hessian matrix. And in the code which you see here now, what I'm implementing is actually the iterative procedure. So I have the derivative or the gradient of the cost function at the value beta k. I have the beta k value, and then I have the new update. Now, normally you would set an iteration criteria because we want to drive this function to 0. But in the code which you see here, I've just set up in a very brute force way a number of iterations because I'm going to play around with a number of iterations. And you will see that the results, depending on your learning rate, are going to be sensitive to the number of iterations which you set up. So let's take a look now at the code here. So it should be pretty straightforward. So what you can see is now I set up my data set. I set up the Hessian matrix, as you can see here, and I calculate the eigenvalues of the Hessian matrix because I want to see what kind of parameters gamma would be optimal for this case here. And here, I actually decide that my parameter eta or gamma, this is actually the parameter gamma, in this case is equal to eta, is now given by 1 divided by the max eigenvalue. And here I just do a very stupid thing. I just set up number of iterations to 1,000 because now I'm just going to play around a little bit. Then I print my parameter beta. So this is my gradient descent. So I have my gradient and I multiply the gradient with beta and I keep updating here. This is nothing but just the plain implementation of this gradient descent method. And this is a starting point. Later, next week, we are going to modify this with other methods like stochastic gradient descent. And we're also going to look at something which is called quasi-Newton methods. So you get a kind of feeling of what kind of methods are out there. And as I said yesterday, one of these methods called ADAM, which is a stochastic gradient descent method, has more than 100,000 citations. So this is a field where you can actually, if you cook up something smart, you can really, yeah, you can become famous here. So I'm just printing beta, and then what I do next here, I actually just compare this with my own linear algebra code, where I just invert the matrix and compare the parameters. So let's just run this code here. And you can see now in this specific case, my Hessian matrix has eigenvalues which do not vary too much, 0.3 and 4.7. And then I have this is my beta 0, and then the slope and the gradient. And this is what my matrix inversion gives. So I'm getting the same result when I'm running through the whole gradient calculation here. Now, note one thing here. So here I have a matrix multiplied with a matrix, multiplied with beta, and I subtract the parameter y. So what does this equation tell you about numerical efficiency and CPU cycles? Any good suggestions? Because this is again one of the bottlenecks. So this, as I said, this is a kind of baby case, right? I have 100 points. So I have a matrix which has 2 parameters beta. So it's a 100 times 2 matrix. So when I'm performing this matrix multiplications and matrix times vector calculations, this is a very small case. So when you do a matrix multiplication, matrix, so I multiply x transpose times x, that if this is a square matrix, this requires n, which is a dimensionality, n times n. It requires n cubed floating point operations. Now, in our case, it's not a square matrix, but still, it's going to require, when the matrix becomes larger and larger, what you see there, this extremely simple implementation of the gradient descent with the one which you see here in this line is extremely CPU intensive if the matrix becomes particularly large, which is not uncommon. So if you have 100,000 data points and 500 features, this is going to be a slow calculation because the matrix is going to be large. So this is something to think of, and that's why people actually try to cook up alternatives to the brute force implementation. So I'm now just setting up the brute force implementation and how simple it can be. But keep these things in mind because they become important, in particular when we are starting to look at neural networks. Okay, and what you saw then is that I basically get the same which I get by matrix inversion. So now I'm running through all the data points. So what I could do next now is simply to say that, okay, let me change this value of eta. So I know that, let me change this eta to, let's make it much, much smaller. And see what happens. And then I'm also going to change the number of iterations to 100. So in this case, what you see now is that the value which I get actually differs a lot. So this is now my prediction. So what you clearly see in this very brute force way where I didn't put in a convergence criteria, and that's the reason why I didn't put it, because I wanted to show you the dependence on the number of iterations here. So this simply tells me I've chosen a step size which is too small. So that means that my search for the optimal value is moving very, very slowly. So it means that if you go back to the whiteboard, so let's take a look at that one and make a small sketch. So in this particular case, suppose now that we have a minimum which resides here. So this is our beta optimal. And we have a function of x, and there we have an f of x here. And now we are searching for this specific minimum. We start with a guess, which places us here. So this is a calculation at the value beta 0, the first iteration. If I make beta too small, no, gamma too small, the step size, I'm just going to move very, very slowly. And after, in this case, after 100 iterations, I may be here. So if you go back then to the Jupyter notebook, what I simply could do now is I could say that, hey, let me now just simply increase the size of the number of iterations here. Let me just put this one just to exaggerate a little bit, just to put it to 10,000. And now it's still not converging properly. So it means that the step size is actually a little bit too small. So let's try to increase the step size. Let's put it to 0.1 here. And now I suddenly have agreement. So what I did now was actually to find a step size which within this number of iterations gave me a result which is the same as standard linear regression matrix inversion, period. So what I want you to have as a kind of takeaway message is that the results will clearly depend on the size of this learning rate which you plug in. Normally, you have difficulties in estimating the second derivatives. So what people end up doing is to have a grid of learning rate values, and then you simply rerun your calculations with these learning rates, and then you see the one which gives you, for instance, the best mean squared error. So what I could have done here would be to have a loop over different learning rates, and then figure out the one which gives me the best mean squared error. And that is often cheaper than calculating your Hessian matrix. In this case, it actually calculating the Hessian matrix is much easier because you just have a 2x2 matrix. And this is something you have an analytical expression for the inverse matrix as well. So you don't need actually here to do these kind of complications which I'm doing here. Another thing you can look at now, so remember the largest eigenvalue was something like 4 point something. So let's put a step size which is equal to 10 and just see what happens here. And in that case, you're going to get not a number. So what will typically happen then is that you will jump down and then you will jump in and out. And at a certain point, you will just jump far away from the curve where it has its minimum. So when the learning rate becomes too large, you are going to, in the beginning, jump a little bit back and forth, and then suddenly it just diverges. And you see this reflected in the not a number here. When the learning rate is too small, you may be still far away from the optimal value for the learning, for the parameter beta. Too simple? Yeah, go ahead.
But if it's always aiming to get to the minimum, why would it jump away? Why wouldn't it just jump back and forth around the minimum?
No, because the values become too large, because the learning rate is too large, so you accrue values which just simply explode. Yeah. Okay. Any more questions? So this is a typical example on how you can play around. You can repeat the same with a scikit-learn if you want to. And this is calls a function which is called SGD, and this is stochastic gradient regressor. And we're going to discuss that a little bit more next week. But I wanted to show you a simple example on what you can do with the ridge regression. So in that case, in ridge regression, the first derivative is actually given in terms of the parameter lambda, which you have here, which is a hyperparameter. And then you know that you can, in this specific case here, it's the same example. You can easily invert the matrix. And you can also calculate the Hessian matrix, which in this case has an additional term, which always, since lambda is larger than 0, it always makes this matrix positive definite, because the matrix itself is X transpose times X, is a matrix which is semi-positive definite. By adding this term here, it will always give eigenvalues which are larger than 0. So that's a matrix which becomes positive definite, and it will always converge. The stationary point is a global minimum of that function. So the only thing you need to do now is simply to add this term with 2 times lambda times the parameter beta here. And that's the only change you need to do in the calculation of the gradient. So if you look at this example here, you simply have now to make a loop over lambdas, and you have this lambda multiplied with the parameter beta. And that's basically the only change with respect to ordinary least squares, because you get an additional term in the gradient with the parameter lambda. And the expression for the gradient is not that different from that. And when you run these codes, you will see that you get the same expressions which you would if you were to run standard ridge regression. So next week, we are going to look at how we can improve upon this simple approach with just a chosen gamma. So this is the simplest way to get started. And then we are going to look at something which is called stochastic gradient descent and look at the philosophy of that. And then we are going to look at different variants of stochastic gradient descent and also some of these more popular quasi-Newton methods, which are used in these type of optimization problems. But the basic recipe which you will encounter is called the stochastic gradient descent. And before we stop here, there is a kind of a shopping list on using gradient methods and limitations. And one of the things to take away is the fact that this gradient descent is very sensitive to initial conditions. They are also computationally expensive to calculate for large data sets. They are very sensitive to the choices of learning rates. And the other thing, which you will notice with these methods, is that all the parameters beta, which you're looking at, they are treated in a democratic way. So that sense that all the parameters treats all directions in parameter space in the same way. So that means that the step size you have chosen, or the learning rate, is the same for all the vectors, beta 0, beta 1, the elements beta 0, beta 1, and so on. And some of them may actually converge faster than the other ones, But with having a uniform value for this learning rate, it means that you will then have a parameter space which is treated in a uniform way when it comes to the directions in space. So as you saw, one thing, it's very easy to implement. You need the expression for the gradient. In this particular case, you have analytical expression for the gradients. When you're coming to neural networks, you're going to calculate the derivatives with the automatic differentiation. So that gives an additional computational cost, but that is an efficient way of implementing derivatives numerically. Here we have what we normally call a very simple case, and you have analytical simple expressions for the derivatives. But these examples are already enough to illustrate the problems you face with the optimization. And that's the main takeaway message. So take a look at this summary and also look at the codes, because next week we are going to dive into the methods of choice in optimization of the cost functions. Okay, should we take a small break for the weekend? Thanks for coming, guys. Take care. Take care.